Good afternoon for today's special event, which will be we have here guests from the CERGE-EI Institute, which is the part of our university, and I will pass the word to the head of this department. So please.
Okay, thanks everyone for coming. My name is MAREK KAPIČKA. I'm the director of CERGE-EI. I'm going to say a few words about CERGE-EI, and then we'll get to our presentation. So I take it some of you know a little bit about CERGE-EI, some of you may not. CERGE-EI is a joint workplace of Charles University and the Academy of Sciences. It was founded in early 1990s. We specialized in graduate education and economic research. So CERGE stands for Center for Economic Research and Graduate Education. So we have a PhD program, which is a US-style PhD program, which means it includes 2 years of courses and then 4 to 5 years of independent work. Besides the PhD program, we have a master's program as well, master in public policy. And of course, besides the education, we do research. We do it quite well. The two other presenters here are PAOLO ZACHIA, who holds the ERC CERGE grant, and FILIP MATÉJKA, who holds 2 ERC grants. So we're quite successful in terms of research. We hire internationally and so on. And those that don't get ERC grants, those become directors. So that's how I ended up here. So I'm going to go directly to my presentation. We thought that it would be useful. There's a lot of overlapping issues or areas. We use mathematics quite heavily in different functions in economics. So we thought it would be useful to present examples or samples of what we do, so that it would be clear what the connections, and maybe you guys would get interested in what's going on in economics. So my presentation is going to be on taxation. So it's going to be about the design of wealth taxes and what wealth taxes will do to the wealth inequality in modern economies. The motivation here could be summarized by this picture. If you look at the wealth inequality evolution in the US, you will see a quite stark increase in at least the top wealth inequality. So what you see here is the share of wealth. The red line is top 1%. Okay, so you can see that the top 1% share of wealth in 1980 was a little bit more than 20%. And after that, you see this gradual increase in the share of wealth held by top 1%. And nowadays we are at more than 35%. And it stagnated a little bit after 2010, but it doesn't really go down. So that's the extent of wealth inequality. And of course, if the top 1% is getting more, then someone has to get less. So here you have an example of the middle 40% of the population, and you see that it's a mirror image, right? So around 1980, the middle 40% held about 35%, and then you see this gradual decline to today's 27, 28%. So there is a huge increase in wealth inequality. There is also an increase and very rapid growth in asset prices. So here you see the Standard & Poor index. This is just from 2016, and you see that it's tripled. That's the tariffs things and so on. That's the dip at the end, but otherwise it is almost tripled in the last 9 years. And so, of course, this situation has elicited or generated a number of various tax proposals. I'm focusing on the US, but there are others in Europe as well. So Kamala Harris, in her campaign, she proposed a tax on unrealized capital gains for wealthy individuals with a net worth of more than $100 million. So she basically took this from Biden's proposal, hence I call it Harris-Biden. Gabriel Zucman, an economist at Berkeley, proposed something similar. He proposed wealth taxes on the ultra-rich, which is people, he defined them as people with $1 billion or more, and he proposed a 2% wealth tax. So those are just examples. There are other proposals. Bernie Sanders and others had similar ones. What distinguishes them, or what's common in them, is that those are nonlinear taxes. They are taxes on only some segment of the population, and they want to tax wealth, and especially what this proposal is talking about, unrealized capital gains. So you don't have to wait until you sell the stock. You would be taxed right away. That's what unrealized capital gains means. And so the question for us economists is, what are the consequences of such proposals, and do they make sense? I mean, the objective of this is perhaps to do something about this picture, or you want to change welfare or redistribute welfare. Does it make sense? So what you need to answer that question is, as an economist, you have to come up with a model that's going to have first realistic movements in asset prices. The asset prices is really the driving force here that motivates those proposals. So you have to have realistic returns on assets, and you have to have some redistribution or distributional effects. Those are the two essential ingredients that you need to have in a model. So that's what I do in this research. I want to develop a quantitative model. This is not going to be just some theory where you solve on paper. I want to have numbers. I want to come up with specific predictions about what happens to inequality and so on. So it's going to be a quantitative model that's going to match the asset price movements, but as well generate a sizable consumption and wealth inequality. So everything I said so far was about wealth inequality, but as economists, we care a lot about consumption as well. So that's a dimension that cannot be ignored. And I'm going to come up with an economy like that, and then I'm going to consider what happens in that economy if you tax unrealized capital gains on top 1%, and that's going to be redistributed to the rest. And then I want to talk about and look at welfare. I'm going to have some preliminary results, but that's I'm not there yet. So here are just a preview, in case you fall asleep, is a preview of what happens here. The nonlinearity in the tax schedule is important. If you don't have the nonlinearity, nothing will happen to any of the quantities of interest. So really, to generate something useful in this economy, you have to have this kind of tax function that only targets a certain aspect of the population. There's a second result that's going to be kind of negative, and that's that the asset price responses will, to a large extent, mitigate the effects on wealth inequality and consumption inequality as well. So what will happen in this model is that if you tax this 1%, well, those 1% are going to require a higher rate of return. So the equilibrium returns in this economy, with assets depressed, you're going to have higher returns. The equilibrium returns will go up, and that's going to go against the objective, the original objective. So the original objective was maybe to redistribute resources, but now the top 1% that's relied heavily on asset returns is going to have high returns, and even though they're taxed, part of that is going to come back through the asset prices. So the type of proposals that that I outlined in the beginning, it's not easy to generate in general equilibrium sizable effect on consumption and wealth inequality. So it's going to be a paper about 1% versus bottom 99%. So this 99% at the bottom, those are going to benefit from the tax. But interestingly, the benefits are not going to be so much from the transfers. So when you think about those proposals, the usual logic is we want to tax the top so that we can give transfers to the poor. That's not how the model is going to work. I mean, it works a little bit like that. This bottom 99% will get transfers, but the transfers are too small to have a sizable effect. Instead, what they will benefit from is the changes in asset prices. So they will become more favorable, and they will gain from them. So perhaps the lesson from this is that we really need to think about what those proposals do to asset prices rather than just mechanically counting how much gets redistributed. Okay, so this is a short talk, so I'm not going to give you a lot of equations, just a few to show you the setup. If it's not on my website, if you guys are interested in this, I can send you a draft, but it's not there yet. So this is going to be an economy, and if you have studied finance, then some of this might be familiar. It's going to be a continuous time economy where the aggregate endowment, the amount of goods that's available in this economy, is going to be exogenous. We call it an endowment economy. So Y is going to be the amount of goods that's available, and this economy is going to be growing at rate mu Y. I have to calibrate this too. Okay, mu Y is the expected growth rate, and then there is some volatility. There are some growth shocks with volatility sigma Y. This is a Brownian motion. dB. So that's how the aggregates in this economy are going to evolve. So anything I do in this world is going to have no effect on GDP here. So that's a restriction. But it's going to have effects on how resources are distributed. It's going to be an economy with two assets. There is going to be a risk-free asset with an instantaneous return R, and then there is going to be a risky asset, which is a stock, and it's going to have a price P. This risky asset is going to pay dividends D. And so DP are the capital gains. If you put capital gains plus dividends, then this is going to be a geometric Brownian motion here with growth rate mu, and volatility of the stock price is going to be sigma. So those parameters here are mu, sigma, and as well the price. They're all going to be endogenous. So this is not just something I am pulling out of a hat. This is going to be justified in equilibrium. This is how the equilibrium pricing function is going to look like, including the geometric Brownian motion. But I'm not going to show you today. We don't have time to show how those stochastic processes are derived in equilibrium, but that's part of it. Okay, so this is about production. On the consumer side, this is going to be a model with finitely lived agents. Those agents are going to be dying at a constant rate pi. So this is a continuous time at each instance. You may die at this rate. If you die, you're going to be replaced by someone fresh. So this is sometimes called a perpetual youth economy because the probability of dying is constant. So if you've lived here for 100 years, your probability of dying is the same as if you lived for 10 years. So it's always pi. So in terms of life expectations, everyone in this economy is the same. It's a simplification, but it allows for certain tractability that we wouldn't have otherwise. This is due to Ari and Blanchard. So the agents are going to be different in terms of age. I mean, even though they have the same probability of rate at which they die, they are still going to be different in age and their past behavior. Besides that, they're also going to be different in preferences. So this is going to be an economy where a lot of the action is going to be driven by the fact that the different types of people have different preferences about risk and consumption smoothing. So in particular, there'll be two types, A and B. A is going to be a fraction alpha of A types and fraction 1 minus alpha of B types. That's going to be constant. That's not going to change. And they are going to be different in terms of risk aversion and what we call the intertemporal elasticity of substitution. So risk aversion is how much you're willing to tolerate risk, or more precisely, the inverse of this is how much you're willing to tolerate risk. And intertemporal elasticity of substitution is something that measures how much you're willing to substitute consumption over time. Okay. If you're really averse to time fluctuations in consumption, then you have a low intertemporal elasticity of substitution. The lifetime utility, I don't think I have to get into it. There's a lifetime utility function where at each instance there's something called Duffy-Epstein aggregator that aggregates consumption and lifetime utility, and that depends on those parameters. So this is going to be different across people. So the way this economy is going to be working is that there's going to be one type. It's going to be type A. They are going to have very high risk aversion and a very low intertemporal elasticity of substitution. So A types, they're going to be very averse towards investing in stocks. Just like a big fraction of the population doesn't hold stocks, here it's going to be because they just don't like the fluctuations. And then there's going to be this 1% at the top, and they are going to be more open towards investing in risky assets because they are going to have low risk aversion. And there are going to be taxes. So these taxes are going to be state dependent. I did tell you what the state is, but I don't have time for that. But it's going to be state dependent and it's going to be nonlinear. I'm going to make it very easy, and I will simply put different taxes on different types. So if you are type I, you're going to face a tax on risk-free assets tau IB, and if you are type I, then you're gonna face a tax on risky assets, tau IP. And dividends and capital gains are going to be taxed at the same rate. That's for simplicity. That could be relaxed. And tax, this is all going to be a tax on unrealized capital gains, just like in the Harris-Biden proposals. And besides taxes, there are going to be transfers across types. There is going to be a government budget constraint here that's going to link all those taxes and transfers. The government budget constraint is going to balance at each instance. That's without loss of generality. And the equilibrium is such that consumers maximize the aggregate demand equals aggregate supplies. And so the usual thing. So let me go to and talk a little bit about what happens in this economy. So you get those two types of agents. One's conservative, that's the 99%, and 1% is more adventurous. So as the economy is going to be hit by shocks, the weight of those two types is going to be changing endogenously. So think of the economy being hit by good shocks, then the 1% is going to be gaining weight, so to speak, because they're going to accumulate more assets. They're going to be more important. They're going to be more important agents in the economy. If the economy is hit by bad shocks, the 99% is going to be gaining more weight. I'm using the word weight a little loosely, but it has a precise backup. So some of those times are going to be are going to look like times of high risk aversion with low asset prices. That's when the 99% gets more weight. So it's going to be like times after financial crisis, asset prices are depressed and returns are high. There are going to be other times when asset prices are going to be high and returns low, and that's going to be when the 1% gains more weight. And importantly, the differences in risk aversion are going to be important in this economy for generating wealth and consumption inequality. As I said before, the low risk aversion agents are not very much willing to hold risky assets. The 1% holds them. Those risky assets are more volatile, but they have higher expected return. So this 1% is going to, on average, is going to accumulate assets faster. They're going to have much more assets than the 99%, just like we see in reality. And that's why there's going to be wealth and ultimately consumption inequality. So this is a quantitative model. You've seen like 5 or 10% of the model. So you don't see the rest. But what we do sometimes with those quantitative models, we pick the parameters so that the model matches certain moments in an economy that we want to replicate. So this is going to be a model that's trying to match some moments in the U.S. economy. It's matching the risk-free rate. It's matching the equity premium. It's matching what's called the market price of risk and to some extent volatility of returns. In this economy, type B agents have 12 times more consumption on average than type A agents, more volatile, but more consumption, and they have 35 times more assets. So we measure inequality with Gini coefficients. The inequality in consumption is just about right. I'm not able to match the asset inequality completely. The Gini is 0.55. The data show around 0.85. But I wouldn't expect to match everything with such a simple model. Okay, so now comes taxes. I've got 5 minutes. So I show one theoretical result. This is mostly quantitative, but I show one result, and that's that if you tax both types at the same rate, and you design the transfers in a way that it does not redistribute resources across types, then this type of tax is going to have no effect on consumption and wealth inequality at all. It's going to have effect on asset prices, but it will simply scale up so that the after-tax prices are unchanged. So in essence, nothing of interest is going to happen in such an economy. So that's, of course, a simple result, but it's telling us what are the channels through which we would expect the taxes to affect the real resources in the economy. It could be either because it redistributes resources, or because it drives a wedge between the prices faced by the agents, which is the nonlinearity. If you've got nonlinearity in the tax schedule, then different agents are going to face different prices. So I will consider one tax reform here. It's going to be a 10% tax on top 1%. That's going to be redistributed to the bottom 99%. It doesn't match exactly the proposals, but it gets in that direction. So what happens here is that, as I alluded to in the beginning, now the type B agents are taxed. So what happens? They require some compensation in the returns, and that's pushing up the equity premium. It's pushing up what's called the market price of risk up. It's simply pushing up the returns in this economy up. There is some effects on the risk-free rate as well, but that's secondary, and I don't have time to talk about that. Overall, the consumption Gini goes down, but only by 0.1, and the asset Gini goes down from 0.55 to 0.54. So it's a very small effect on consumption and asset inequality. Interestingly, now I've got the economy. I can do all sorts of experiments. What I can do is to shut down all the changes in asset prices, and I look at the partial equilibrium. So asset prices are being fixed at the benchmark level. If I do that, I see much larger effect on consumption inequality. So the ratio of consumption of the two types on average is going to go from 12 to 3.37. Instead, in general equilibrium, it goes to 9. The mean asset price, mean assets ratio from 35, it goes to 8.8. In general equilibrium, it goes to 0.32. So the prices are really key in understanding the small effects. And final slide. I look at welfare. How are those two types impacted by this tax policy? The type A agents, they still get a sizable welfare gain from this. Even though it's not seen in the inequality measures, they get about, the way we measure it is in consumption equivalents. We try to translate the welfare gains into percent of consumption, so they get about 4.7% gain in welfare. But interestingly, it doesn't come really from transfers. If I only isolate transfers, they do get a welfare gain, but only 0.4%. Most of the welfare gains are coming from the price effects. So that's kind of that's not what we usually think about, and it might be a bit counterintuitive, but it's a different channel than I guess those proposals have in mind. the lessons here, perhaps for policymaking, is that maybe we should pay more attention to how those tax proposals move the asset prices, and less how much they collect and how much is redistributed, because the movements in asset prices turn out to be more important than the transfers. I'm out of time, so I'm going to stop here. And I don't know if we have time for questions. I don't want to dig into your time, but sorry, Philip's. Yeah.
It's their time.
Yeah.
So I have two questions as a non-economist. So the first one would be, how did you validate your model? In a sense, it's very simplistic model. So against what empirical data?
Well, I mean, this is in the calibration. So there's a standard procedure. Where is it? Later. That it's not a model that's estimated. It's a model where you target certain parameters, not just those, but there are other parameters as well that I don't show you. Sorry, you target certain moments, and then you choose the parameters of the model, so that the economy looks like the U.S. economy.
Okay, and my second question would be about the dynamics of the economy, right? We have seen in your data that inequality basically began to rise at the mid to end 1970s, and has more or less kept rising, I guess.
Yeah.
And so what is responsible for that? And does this, in your opinion, as an economist?
Okay, so it's not in this model. I should say that it's not in the model, and I don't think the forces even have a potential in this model. I mean, it's technology changes are important. I don't really have them in the model. To a lesser extent, foreign trade. There's a lot of talks about the China shock, especially in the early 2000s. That's not in the model. So this is for motivation, but it's not a model that would explain what's causing this rise. We've got other papers for that.
Do you have any results on control stuff for this model? I mean, if some of these parameters would be control parameter, resembles a little bit some infinite time horizon control parameters that we studied here. So, I mean, things like the Hamilton jet probably well manipulation for this stuff and so on. Or if you did anything mathematically on that.
Yeah, no. So that's why I said you have only seen about 10% of it. There's no time, but the way you solve it, okay, let's, the equilibrium, so it's consumers maximize utility, so there's an AJB equation for that. So I'm solving that part, and then all those equations, they're part of the equilibrium set of conditions. So I'm kind of solving that jointly, but there's an AJB for this, and it's got one state variable, which I talked about the weight of the type A agents. That turns out to be a state variable. So it's a one state variable. There's some normalization, but it's a one state variable HAB equation. That's in the core of this. Okay, I think I'm gonna stop here. Thanks a lot, and I'm gonna give this to Philip.
Thank you. Thanks a lot for coming. Thanks, Marek. So at the beginning, when Marek said that we are US-style department, I was wondering, does he mean that we change tariffs by 100% from one day to another? That we want to take over Hungary, and that we expel students to third world countries? We don't. And then your questions were great. So actually, a big part of macro is based on those equations, dynamic macro Bellman equations, and And Marek didn't talk about it, but his work especially is, no, he would tell you better like what methods when he solves for optimal contracts using variational calculus and stuff like that. By the way, he was very humble at the beginning. He's the best Czech macroeconomist here. So what do I do? I don't want to talk about Marek's stuff. I wouldn't understand it. Okay. Is that it? Yes. So Marek talked about the big stuff, and one of his main points was that the proper macroeconomics is that they're interacting parts, interacting markets. You can have labor market, asset market, product market, and if some people in the media or politicians just say, maybe we can just change this thing and it solves everything. If you account for interactions, maybe the final result can be very different. That's why macro is important and beautiful. I'm going to talk about something different, about the micro level of human decision making. This is a project, and those will be just pieces from the project with team of great colleagues from Berkeley. Economics at some point started venturing out. We felt like we don't have enough interesting questions, but maybe we have some methods. Sometimes they are simplistic, just like you said, but we try to understand very complex world. So we use sometimes simple models that we want to understand, the world at least a bit better in a specific simple dimension. So for us, because all the models are based on, we're trying to model human beings, people that decide to consume, buy, and so on. So we want to understand the decision making better. So we've been asking questions. How humans in this project, it will be how physicians, which they think, how they decide, what they know. We do have theories. Very often when we measure this, we just do simple things in lab. Lab for us is a classroom of students that solve simple tasks. When we venture out to the field, it's more complicated, very often. So we'd like to understand how people think. Do people differ a lot? Do these frictions, when I say frictions, I mean imperfections of thinking. Do they matter for some of important stuff where people decide? For instance, when doctors decide on how to treat patients. We can also ask questions, if doctors get a lot of information, is it useful for them? Do they understand it? And so on. So I'm going to show you, by the way, I used to be a student here. I used to be a physicist or a mathematician. Probably even back then, Libor would say that I was not, and I maybe agree. I have a degree in applied math, but that's been 20 years ago or 15 years ago. I'm a mathematician less and less. You will see almost no math here. There is math behind, but it's important. I think what I wanted to convey is that math is useful, and there are ways how to do it much better, even if I cannot do it. Maybe you can, or you can help us. So very often, when we want to understand how people behave, we have to combine simple models with data. That's also related to your question about Marek's, that the model seems simplistic, but you start with something simple, you see how it behaves, you relate it to data, maybe then you change model. So it's never-ending discussion between model and data. So you see a super simple model of behavior. Then we use some simple statistical inference. We look at data and we try to infer what people think. You'll see how we do that. And then also, not what they think, but maybe what they could think based on the information they get. And there might be some differences. Okay, so ideal setup for that, how to understand how people think, is that we'd like to have complex world of a lot of things people could do, a lot of things would be optimal for them. So here it will be a lot of possible diagnosis of patients. There will be patients coming to emergency department, emergency room, and physicians will have to find out, do they have heart attack or just fever or thousands other things. Repeated situations, that's important, that you have a lot of patients coming in and many of them have the same thing, and you see how doctors behave in perhaps the same situation. So that's when you can start getting some good statistics. That's super difficult in macroeconomics, right? Because there maybe you have Great Depression just once, and then you have to wait 100 years for another data point, hopefully, right? So ideal setup for this would be repeated situations, hopefully situations that matter, because that's what you want to understand, and so on. So what we do in this project, we study how physicians decide. So there's a patient coming to emergency department. There, let me jump here. Nurse writes name of the patient into the system, and from there on, we basically see everything that's done with the patient. We have a lot of data from American hospitals. We see what diagnostic tests the physicians ordered, something like they ordered, measured blood pressure or did some chemical test of the blood. We see results of the tests. We see a lot of things. We see when this happens, who does it, and so on. How do I go back? I don't know. Okay. So the applied part of this project could be, we care about healthcare in the end too, right? So in healthcare, we know that there are big differences between how people end up interacting with the system. Some get good care, some get bad care. Sometimes it is that they're from rich neighborhoods versus poor neighborhoods, but sometimes it can be just because the particular physician sometimes performs well and sometimes makes errors. That's what we study here. So what role does the process of diagnosis play, the decision-making itself, and how much variation there is within physicians? So what we do here is that we, for instance, look at when the physician gets tired. The physician gets complicated patients, maybe has to think a lot, and then 30 minutes later makes mistakes or decides in a very simple way. We talked about this. This is a screenshot of what the physician sees about the patient. The physician can look at medication, test results, can input orders, and so on. And we have all that in our data. I'm not even going to call it a model. I simplified it to way too much, so let me just call it a conceptual framework. We often do that. We try to write a simple model just to fix ideas how we think about the behavior, and then we can look at simple dimensions. So there's a physician that faces a patient but doesn't know what the problem of the patient is. Let me call that an unknown state of the patient. State is D, that's the true diagnosis. The physician has some belief about the diagnosis. We can model that by subjective probability distribution of over the diagnosis and wants to find out what it is. So we like to narrow the distribution down, ideally that all the mass, probability and mass is on one diagnosis so that the physician is sure what the problem is. For us, what's crucial is that the physician learns, gets signals. That's how we model. Information, and refines beliefs. The physician here chooses how much to think. Thinking here can be mental signals, so looks at the patient, looks at color of the eyes, maybe asks questions. That's something outside what we don't see in the database, and then also orders external signals, X-ray, blood test, and all these things that we do observe. So thinking and doing, and then decides what to do with the patient. You can also decide to send the patient to a hospital. So very simply, there are many possible types of diagnosis. Let me assign some probabilities to them. We can start with the uniform distribution. Physician runs a test. Of course, in practice, this is much more complicated. The distributions are smeared, noisy, and so on. But here, for sake of simplicity, let's say it's just a binary partition. All diagnosis runs a test. Maybe the result is low blood pressure. Rules out these diagnoses, probabilities left just on these, and so on. So learn something. You can run more tests. Some of them can be thinking or just interaction with the patient. Some of them can be the ordered diagnostic test. So narrow something down. This would be the final posterior knowledge upon which the physician decides. again, in a super simple way. In economics, it's not clear exactly what definition of economics is. Some people say it's just a science about how to allocate scarce resources. So there are always some trade-offs. It used to be money or people that worked. Here it can be your mental capacities or effort. So we would start with some simple way of how tiring it is to think and how costly it is to order X-ray and something else. And you can choose, the physician here would choose how many of these external tests to order, how much to think, and then what treatment to prescribe. Let me not talk about this. Kind of super simple. The only thing that I want to talk about is that there is some cost of thinking that increases if the more the agent thinks, the more gets tired, and the costlier it is to think. Super simple implication here would be if the physician is already tired from thinking, had to think more, then in the future chooses to think less because it's costly. It's like if Apple is more expensive, maybe you rather buy Pear. Then if thinks less, the result is also that knows less when stops thinking, orders more of these external orders, and makes diagnostic tests that are more typical. Typical, it means that fit more types of diagnosis. It's like measuring a temperature, while testing a blood, testing a heart attack is for more specific types of diagnosis. This is everything that you're gonna see that we will see in the data. There's not that much time, but we will see that this happens. By the way, our Minister of Healthcare about 2 years ago wanted to proposed a reform that younger doctors would have to work longer shifts. And he thought he would save money on wages. The results here show that, yes, you do save money on wages, but they make many more orders of these external tests. So they stay longer, but because they don't quite understand what the problem is with the patient, they rather order X-rays and so on. So, you would never save money on that. This is an important thing. At the beginning, I was saying that from the data, we try to infer how people think or what people know. How can we do that? I'll try to explain it with this very simplified concept. So imagine that first the agent thinks, finds out these are the diagnoses, and then there are two types of external tests that we can observe. Sometimes the physician orders X-ray, and sometimes just orders blood test. Exposed, because in our database, we see what the problem was with the patient. We see what the diagnosis was. We see what tests they ordered. So we can look at the conditional distribution of, let's say, anytime they ordered X-ray, what the true diagnosis was. And we see whether that distribution was very broad or very narrow. So for instance, if we see that every time they order, what is it called? Troponin test, something like this. It's a test for heart attack. Then it's either one of two diagnoses in the end, so the distribution is very narrow. Then we can infer that the physician already knew quite a bit. So you look at this distribution of diagnosis conditional on the action that they made. So that's how we can actually from this data infer what the physician thought the diagnosis was. Okay, in our data we have the diagnosis, treatments. I'm not going to talk about cognitive load, and we can infer knowledge. We can infer what the physicians knew, and it is data from hospitals in California over 3 years. Cognitive load to us is something like how much the physician had to do for a patient or how complicated the patient was. So first, it depends on type of patient. It depends on acuity level, how severe the case was, what the diagnosis was, and so on. And this is, you see, those are different trajectories for different shifts of particular physicians. That the highest cognitive load is in the middle, less at the end, so on. So it's like cognitive load of last 60 minutes. I'm going to show you a few results. So first, there is some simple model of behavior behind. the model is a bit more complicated than what you saw, but much more complicated. The basic logical implications are similar. And then we have these elements of data. We want to study connections between them. It can be, sometimes it's just a simple regression. Here it would be, we see that anytime cognitive load goes up, that means the physician had a complicated patient, then on average, with future patients, they think less. That means that the reduction of the uncertainty, what they think about the diagnosis, is lower. They're tired, they think less, they just make these orders for, maybe they just measure temperature all the time. That's one thing. They make more diagnostic orders, so they use more of these external resources. They spend more, let's say, money of taxpayers and so on, because they're not sure. What they also do, because they're not sure, they send the patients more to the hospital. If they don't know what the problem is with the patient, physician is tired, just to be sure, say, we should send the patient to the hospital, not home. Of course, if you have these issues, you can start playing with it. So here we did a simple exercise. What if we assigned patients to the physicians differently? You can imagine that there is a lot of patients, and in the emergency department, there is 12 physicians. You can say, if this physician is tired, maybe next patient should go to that physician. And we know how they behave if they are more and less tired. So we can do a counterfactual exercise. Of course, it's simplified, it's not perfect, but we see that you would save on resources, you would send less patients to the hospital. In a future, in a follow-up project, we even study health outcomes, which is something like readmission within 30 days. If you send them home, well, they become sick in next 30 days because maybe you misdiagnosed them. And we see some effects there. A few minutes only, I'm going to skip this. In general, we see that those physicians who are tired, they think less, they use diagnostic tests that are not targeted well enough, so they acquire information in less targeted way. I'm going to skip this. This is perhaps a bit more interesting. There are lots of different tests for health outcomes. So physicians have hunch, maybe it could be this diagnosis, maybe that diagnosis. So there is a particular test, but different physicians have different success rate of that test. Maybe Sherlock Holmes would say, now I should test heart attack. And then the test would have a higher rate of returning a positive result. So for a given test, maybe average success rate or this positive rate is 0. You can plot distribution of different physicians. Some of them are have higher positive rate than others, some of them lower. You can ask which ones. These are those who use a particular test a lot. These are those who are successful with the test. So typically those who use some test a lot, they're more successful with it, and the other way around. We don't know which way the causality goes. We don't know whether they use a test because they're good at it or the other way around. That they're good at it because they used it a lot last few years. So there is some experience and so on. But we see big differences between doctors. Okay. So this was how we can infer what doctors think about patients and how they think about them in different situations. We can also look at it a bit more. You can do inference from, if you know properties of the stochastic tests, you can do some Bayesian analysis, and you see that given the sequence of test results, you can reconstruct of what the physician could have known. Maybe doesn't know, but could have known. So for that, we just need the joint distribution of a particular test result in diagnosis, and that's the Bayes law that you know. I'm gonna skip talking in simple way about Bayes' law, but it's basically if you have the empirical joint distributions of the test results and the underlying state, you can infer how much you can potentially learn from observing positive versus negative results and so on. So then we can simulate things like this. These different numbers are different potential diagnoses. They have names. I don't remember which one is which. And then we can study for a particular encounter that the physician could have known this, that this diagnosis had almost probability 1 and the others. So well, this would be another encounter. Encounter is that one patient comes to one physician and stays in ER until is discharged. In this particular, at the beginning, there were test results that pointed to this diagnosis almost with probability 1, but not quite. But then more tests revealed that actually that's not the true diagnosis, and another one was the true. We don't know yet that whether that's what the physician really knew, because for them it's very difficult to do Bayesian updating on the fly. Maybe this kind of, if we provided this information to them, it would help them quite a bit. But we do see that physicians that order, physicians that order tests that are more optimal, so that on average they can learn faster, they have better outcomes. Outcomes means that, for instance, readmission in 30 days for their patient is smaller. So if you're lucky and you're assigned to a physician that chooses the signals, the specific tests in a way that on average they converge faster, you have lower probability that you have to come back to emergency room in next 30 days. Again, there is some very simple statistical analysis behind that based on Bayes' law and a lot of data. This would be another case. So you saw, well, application here seemed like it's not economics, or for others, you know, we love economics because it allows us to think about a lot of different things. Very often our work is some combination of simple assumptions of what we want to study and how people maybe behave. Ideally, I showed you a particular model of how we think people behave. Sometimes you would allow for more freedom. Maybe you would say, the more they think, the more difficult it is for them, or maybe the easier it is for them. We don't know. So there would be a parameter that you would try to estimate from the data. Here I just showed a simplified version. It's just that let's assume that that's how physicians behave. And then we combine it with data. Often the theory should allow us to understand the data better. And then the data tells us whether the theory makes any sense. And hopefully, and so that's what we did here. We inferred what they think, and we found out that when they're tired, they think less. We can even say, you know, what were their hypotheses. And we can infer what they could have known. Thank you. So, any questions?
I have one.
Thank you.
Is physicians, how you have chosen this? Is it because it generates nice data or other reason?
First, yes, data. So for a long time, I've been working on how people acquire information. We develop theories, but there isn't much data. So we looked for ideal setting where you have repeated situation. Here it is somewhat repeated. So every time there is a new patient that seems the same as the one before, but you have to find the differences and the data. And the second, something that matters, and somehow here I couldn't get excited by, yes, let me not talk about, give examples of econ projects I could not get excited by, but this was something new, and we thought that it could potentially matter if we find something else. So both of these things. Yes, Libor.
So what is your advice to the doctors how to do better?
Thank you. We don't quite know yet, but so what we are doing now. So there is some advice for let's say, the management of the hospitals, that we can assign patients to physicians in a different way. That would be one. Then the question is how to, we see when they start making mistakes. So the question is how to help them. One would be to provide them with information in a different way. So they have all these IT systems now, and the physicians hate it, actually. They say, it's too much information, I cannot look at it. Often they get alerts about allergies of the patients, so they don't look at it at all. So if we found a way how to summarize the information for them, so for instance, that would be this. At a given time, if we just told them this diagnosis 90%, this diagnosis 6%, and that it would be a good summary. Well, instead, what they know is they ran maybe 10 tests. They see these tests, and for them it's difficult to combine it together. So that would be one way how to provide them. We haven't tried that yet. We're thinking about an experiment in those hospitals. There should be other things, but yeah. Important questions. I don't have great answer yet, but this is the direction where we're going. I think there was one more question, so I'll have one more question than Marek, than our director.
What are the events? Because I can see there's a lot of them. So.
Yeah. So this was me being lazy. Those are all the things that we see in the data that happened somehow. So those are not just events that every single time they get new piece of information, but maybe nurse did something on the patient, and maybe even something happened to another patient at that time, and so on. So these are just, that's why I call it events. It's not even time and so on. So this is, we could not send it to a journal in this form. Very good. Thank you, guys.
So thanks everyone. I'm Paolo. I get good vibes by this place. It's nice to be here. I was here.
Paolo's shirt, by the way.
You can see it later if you like. It's a shirt with math symbols and graphs. I only use it on special occasions. Speaking of which, last year I came here to give a couple of seminars on economic networks. And I did not have the chance to finish what I wanted to say last year. So so I'm a little bit of a completionist. So what I'm trying to do here today, so the way I interpret this event is a chance for me to show what I wanted to show last year and to show at the end why it matters and how is this a frontier topic in research and how it can benefit from advanced mathematics. That's my understanding of how I can best use my time today. And in the last slide, I will connect that to my research as well. So let me introduce a real-world problem. These are two articles from The Economist and the Wall Street Journal that speak about the disruption of supply chains and their macro consequences. Everyone knows that inflation is due to the pandemic, the war, but why exactly? Because supply chains got disrupted. Firms at some point failed to trade with other firms in other countries through which they will gather their inputs for producing goods that get to our markets later down the line, and that caused the price increase. This is a big topic, but we don't really know how to handle this. So the policy discussion and the understanding of economists on this topic has been a little bit limited until recently. And there has been a lot of talk on how to handle supply chain fragility. Can policy help firms go back to yes?
I'm sorry, can you stand on this part because there is the microphone.
Oh, I apologize. I was not aware of this. Okay, yes, sorry about that. And I'll try not to move. So what can we learn from economic theory, and what mathematical tools can we devise to figure out ways to push firms towards better networks that make our lives better later down the line? And this is a very hot topic right now in the profession because of a paper that came out recently that uses tools from like algebraic geometry or something like that. Don't quite remember the name. We'll talk about that at the end. So let me give you, first of all, like an overview of the topic I wanted to cover last year, a model of network formation. So this was published recently by the recent Nobel laureate Darren Acemoglu on a major journal in the profession. I will give you a flavor of how the model looks like. It's not a model of mine, unfortunately. And just hopefully you will understand how elegant this is. So it's a model where we have n+1 firms, where those firms produce their output in a very general way. So this output combines inputs that come from other firms, it combines labors, and it has these inputs are combined with a very general production function, as we call it, a function that transforms inputs into output. But the question is, who are you getting your inputs from? So in this model, the authors actually come up with a game that specifies how firms choose their trade partners. And therefore, they lead to a network or a set of supply chains as an outcome of this game. So this game works like this. It's a sequential game. I assume all of you know the basic of game theory. So the firms pay costs at the beginning if they want to become either customers or sellers of other firms in the same economy. Now, you create a link only if the two of us pay the cost. I must pay the cost for being a customer, you pay the cost for being a seller. That creates a link in the network. If we get a link, then we establish a contract that specifies, conditional on the network, what is the price of the inputs of the goods that I sell you. So I'm a car maker, I need tires. I want to buy tires from you. If we are a link in the network, I need to pay a price for each set of tires. And lastly, production occurs, and the firm number 0 sells all the consumer relevant goods to the final consumers. And those consumers use the income they get from being workers or from being owners of the firms to buy this. This is what we call in economics general equilibrium. I'm not focusing on this. So just to give you a sense of how elegant this is solving this game puts together tools and ideas from game theory that economists use a lot. So if we denote an adjacency matrix as capital G, the collection of all links in the economy, we can think how this is solved by backward induction. So at the very end, we take the network as given, we take the contracts as given, and then firms produce by maximizing their profits. This is very standard in economics. It leads to what we call a general equilibrium, a situation that I will summarize in a second. Then at stage 2, firms that have agreed to become partners, they decide on their contracts using a concept that is known as Nash bargaining. And it's a famous solution concept from cooperative game theory. And going at the very beginning, you pay the price to become a customer or a seller of any other firm in the economy if you anticipate that that's going to be convenient for you. So what is an equilibrium here? It's a solution of this game where the supply and the demand of all goods meet. It's a classic concept in economics. Firms maximize their profits, and they do not want to change their position in the network, meaning that they do not want to stop being partners of firms they are partnered with, and they do not want to become partners of firms they are not partners with yet. So what do we learn out of this? Well, we learn a bunch of things that are relevant for the real world, but they are limiting in a way, and they are limiting in a way that calls for more research and calls for more advanced methods, as I was arguing. So very briefly, we need to kind of figure out what are the features of the possible solutions and how many solutions are there. Obviously, some solutions are not good because they are not going to be convenient. Oh, there is a typo here. On the right-hand side, you should have this AG. So basically, this is what is AG is what we call aggregate network productivity. It's a property of the model that basically say, given a G, given a network, what is the maximum output you can get in the economy? Obviously, this maximum output cannot be less than the total cost of creating those links. So a G that satisfies this inequality is called a feasible network. And what we learn from this is that, well, this game has multiple equilibria. A standard result in many models in economics, but one that challenges policy a lot. And the basic problem that we have is that if there are multiple equilibria, how do we as policymakers figure out strategies to give firms the proper incentives to stop, break links that disrupt international trade, that disrupt the well-being of people through higher prices, for example. And this is a classical combinatorial problem that has analogs in the econometrics of games, which is the field where I am working, actually, and statistical physics, too. So we can learn a few more things from this game. So suppose that we introduce an assumption to the primitive I was talking about earlier. So we suppose that the economy is so-called supermodular. What does it say? Suppose that we have two potential feasible networks, G1 and G2. G2 is a subnetwork of G1, meaning that it contains links that are in G1, but possibly not all of them. Well, this property says that if we add one extra link to G2, the effect on total productivity, total output in the economy is higher than if we added an extra link to G1. So this comes naturally from many standard assumptions that we use in economics, like, for example, constant elasticity of substitution, production functions, something I'm not going to elaborate on. But the thing is, this very simple assumption that is not really adding a lot of machinery in this model gives us a lot of some very meaningful results that match our understanding of the crisis. So I took some results from the paper that I condensed into simpler theorems just for the sake of illustration. The first one says that under supermodularity, we do have many equilibria, but they are a lattice under set inclusion, meaning that, well, at the end of the day, there is going to be a large network that I call G star, which is a potential equilibrium out of many, and all other equilibria are subnetworks of G star. At the same time, G star is the equilibrium with most profits and output, but it's also inefficient. And I'm getting to that in a second. And another result is that if you increase the cost of creating links at G star, then you are going to decrease profits and output throughout the economy, which is intuitive. Now, let me give you an illustration borrowed from the paper. So what this model does is to capture ideas that popped up in the discussion in The Economist, the Wall Street Journal, and other newspapers, but that no economic model had delivered until the point when this model was developed. So first of all, this says that denser supplier chains, so networks that with lots of connections, and some of these connections are very central because they facilitate link across very distant places. This is really reminiscent of nowadays supply chains. Well, they increase the value, yes, but they also increase the market power of firms. What's the intuition? The intuition is that if I'm a very central node in this network, then I become very valuable. And at the stage number 2 of the model, which is the stage where I need to, bargain on the contract, then I am going to be in a better bargaining position, and I can somehow threaten to, not to establish a good contract for you unless you give me the price that I want. And in this sense, this is inefficient. Even the best network here is inefficient because of this, as what we call this friction, this market failure in a sense. And the second fact is that networks that are denser are more fragile. Why? Because let us take a very simple example. So this is a simple network where J sells to I, and this is a denser or even fragmented network, using the terminology in the paper, where J sells to I only indirectly through a partner that they have in common called K. Now, what happens is that K becomes so important here that it can somehow extract more value from the economy than I and J can, even though this network as a whole generates more output. It is more productive in general. So what this means is that if we plot aggregate output as a function of the costs to establish a relationship, this function will be a discontinuous one with an interesting property, that there will be a region where the output for the integrated network will be higher, a region of the fixed cost. In this region here, the output of the simpler network is higher. Why? Well, what happens here is that the threshold at which firms decide to stop trading with the K firm is lower, because the K firm has a very high market power, and an increase in this fixed cost can collapse the equilibrium where these three firms were trading together very easily. While the threshold that will break the simpler network occurs at a higher value of the cost. And this is a way to think in a very stylized sense of what has happened following these major shocks that changed the economy in the last few years. Now, where do we get from here? So I have like 5 minutes maybe. So I think I have 2 slides. I'm actually going faster than I thought. I want to introduce you to a framework very briefly that will help us think on how we can design incentives to enable firms to keep the right relationships. Now, this can sound a little bit, how do you say? There's a word that escapes me at the moment. Paternalistic. Why would we as the government mandate firms to behave in a way or another? Well, I'm not that in favor of command economists, let's put it like that, but probably we can give general suggestions, like pieces of advice in a very indirect way. But like Marek talked about tax policy today, and we can probably use taxes in a smart way. I'm not getting into the philosophy of that. That's very interesting, but that's kind of the perspective I'm taking. So this is a picture from a video game that, according to statistics, many people play in the Czech Republic. So the point of this video game is to take a country, establish companies, and link in them in a way that is more efficient. And people came up with spreadsheets to actually figure out what are the best strategies to play this game. I take it from the audience that some people here have seen this video game somehow. It's called Victoria 3, by the way. Now, the point here is the substantive economic question is to do this in the real world. So, I kind of discussed this. So, there has been another paper that in the last few months has caused quite a stir in the profession, because it suggested to use tools from algebraic geometry that were not known by economists, let's put it like that, to solve a long-standing problem in a related field, which is also a field that I'm interested in, which is economic geography. So there is a very close connection between this problem and the one I'm talking about. So let me illustrate what this, in one slide, what this paper has done and how this relates to the problem, which is still an open question, that the policy problem that I'm conveying now. So this is a job market paper from a student, from a PhD student from MIT, and it's a paper about industrial policy. And in particular, industrial policy interconnected with economic geography. So in economic geography, we have a problem that's not very unlike the one on networks, which is basically how do we best allocate firms and people in space in a way that's inefficient. Like, why are there cities? Cities are there because it's easier for people to meet and produce. But there are complications, but basically this is another environment that features multiple equilibria. So suppose we think of this problem as a system of nonlinear equations that look like this. We have a vector of endogenous variables, like firm decisions whether to be present in a place or in a market or in a city or not, and S are exogenous variables like firm costs that are specific to a place. So this function f is nonlinear, and obviously finding solutions for nonlinear problems like this in general, like for moderate dimensions of problems like this, can be very complicated and expensive. However, in the field of nonparametric econometrics, we have tools that under appropriate conditions you need the right data, the right quote-unquote instrumental variables, exogenous shifters, however you want to call them. They can let us figure out what f is, or at best, a polynomial approximation of f. Now, what people figured out recently, and I will be curious to hear if this is obvious to you, it was not obvious to us economists until recently, is that we can use tools from algebraic geometry. That was the phrase that escaped me earlier. For example, total degree homotopy continuation to enumerate the number of equilibria in a system like this. Like, well, I'm not talking about solving this. I'm talking about telling how many such equilibria are there. And like if I understand correctly, the method, you start from a system that you know, and you start deforming the system increasingly until you get to this discontinuity in the number of solutions, and so on and so forth, until you approximate the function that you knew was number of equilibria you are wishing to calculate. And then if you do that, you can, other additional tools that are illustrated in that paper, attach names to those equilibria. If you by following the algorithm, you can somehow trace some properties of the solutions, like y, for example, an average of y. And you can add names to these properties. You can say that some of these equilibria are bad, some are neutral, some are good. So this is very useful because from the point of view of empirical economists that need to suggest policymakers for policy tools, we can say, oh, look, suppose that S is a set of variables that policymakers can manipulate, like taxes that apply to different firms at different places. Well, somehow this can help us predict if manipulating taxes in one direction or another direction will shift the economy towards a good equilibrium or a bad one. Now, how is this related to the problem I was talking about earlier? This kind of setup is easily recognized not to be unlike the one of endogenous network formation. Endogenous network formation is a way to think about it in a similar way as in the previous slide, is to think of the probability of creating a link conditional on some characteristics of firms' X's or policy variables as a function of the rest of the network itself. Obviously, this problem is going to have many solutions. Now, however, so you can kind of get where this is going. By the way, I'm working on empirical econometric models of this kind, where, however, I need to make assumptions on things like the technology of firms or the preferences of people to minimize the number of multiple equilibria, at least in a local neighborhood of a single unit, of a single node. Otherwise, this is not going anywhere. But maybe I'm not good enough in mathematics. Maybe I do not know algebraic geometry yet. So the problem with this is that this is, in general, with networks of moderate size, the number of multiple equilibria is too large, and even homotopy continuation might not work well, like fast enough for us. So in my work, what I do is to sometimes split the network and focus on subnetworks where I can simplify the solution. But probably what is necessary is to do more research and probably study what more advanced mathematical tools can help us solve problems like this that are very at the frontier of economic research, and they are really at the frontier of the policy discussion. And that paper on industrial policy I mentioned, it became extremely popular in a couple of weeks as soon as it came out, because it addressed an important question that people had been stuck for decades. And I guess there is a lot of room for people who are willing to contribute to this area with the right knowledge and the right understanding of these tools to actually come up with something smart. And this way I'm done, and I hope I put closure on the seminar I had last year. Okay. Okay. Questions.
Does it make sense to make any kind of calibration as
So,
in this area?
like the way I would interpret this question is, how do we come up with G? Because here we can take data on many cities, many markets, and use those tools from non-parametric econometrics to approximate F. But how do we learn G? That's similar to what Philip said earlier. In macro, you only have one data point at a time. Here, we only have one economy at a time. So here, what you should do is probably, make assumptions and calibrate numbers or estimate numbers some other way in order to recover G. But this is it's a separate problem from the one I'm talking about. Suppose you know G. How do you enumerate the equilibria, and how do you get a sense whether a manipulating X can lead the economy towards a better or a worse equilibrium? That is an open problem. Yeah.
In fact, we didn't nominate anyone to conclude the seminar today, so I will take this as dictator. So, is there any other question? It seems that not. So, the initial idea to organize this came from me, and then to Marek, and then to others. So I'd like to thank those from MATFIS who helped me and us to organize this. The idea is simply to inform you what we do, how we use math, and hoping that there might be even some collaboration between professors, students, because we need math and you need some applications for your math. So this was the idea. I hope it will survive longer than this day. Thank you very much for coming.